Nuclear reactions occur with a timing called half-lives. The concept of a half-life is very straightforward. It means the time it takes for something to be half gone or half changed. We have half-lives with the concentrations of drugs in our body. We can have half-lives of herbicides and insecticides in our environment. There's a lot of ways that we can see the whole idea of half-lives occurring. So this is an important concept for you to understand.
The way that radioactive isotopes undergo reactions is very specific and follows a pattern that we call radioactive decay or exponential decay. Radioactive isotopes decay through what we call half-lives. Let's look at an example of a half-life occurring. If we have 16 grams of phosphorus 32, the half-life of phosphorus 32 is 14 days. So in that 14 days, half of that 16 grams decomposes. It becomes sulfur 32. So only half of the original amount of phosphorus 32 remains. That's called the half-life because that's what the time it takes for half to decay. When another 14 days occurs, half of this 8 grams then is decomposed again. Now there's only 4 grams of phosphorus 32 left, and of course it becomes sulfur 32. Another half-life occurs, and you can see that phosphorus 32 then decays from 4 grams down to 2 grams. So now figure out from seeing this pattern how much will remain after 14 days occurs, how much of the 2 grams of phosphorus 32 will remain. You should be able to say, well, it's going to be half of 2 grams, so it will be only 1 gram. And this is the method of how all radioactive isotopes decay. Now, the length of the half-life differs for each isotope. One isotope may have a very long half-life of, let's say, 3,500 years, and other half-lives may be shorter. For instance, there may be another half-life that might just be a few seconds. So each isotope has its own particular length to its half-life, but they all decay in the same method in that half goes away when the half-life occurs. So here's an example of how a problem could be asked on this. It says if the half-life of iodine 131 is 8 days, how much of a 100 milligram sample remains after 32 days? The first thing you have to do is determine how many half-lives are occurring. 32 days is 4 half-lives because there is 8 days in 1 half-life. This means that the original amount, the 100 milligrams, is going to be cut in half 4 times. So we can write the 100 milligrams and then cut it in half 4 times. So if we look at this, it would be 100 times 1 half times 1 half times 1 half times 1 half, and you would see it would be 6.25 milligrams as your final mass after the 32 days has occurred. So now you've seen an example of how to do this. Now what I'd like you to do is look at this problem, read it, and determine how much of the isotope, or of the isotope labeled compound, remains after 5.5 hours. If I look at 5.5 hours, that's 330 minutes. 330 minutes is 3 half-lives. 3 half-lives means that the 0.25 grams of the fluorine-17 labeled estrogen will be cut in half 3 times. So it's going to be 0.25 times 1 half times 1 half times 1 half. That gives you 0.031 grams. The measurement of radioactivity and how much is absorbed is very important to us because it can be so damaging. There are a number of ways of measuring radiation, but the two that are most important in the biological area are RADs and REMs. Now, a RAD is the radiation absorbed dose. It's the amount of radiation that would be absorbed by a gram of material from a particular source. But this is variable in the amount of damage one rad will do depending on what type of radiation is coming out. For instance, beta particles are more damaging than alpha particles, and gamma particles are way more damaging than beta and alpha particles. So there's another type of measurement of radiation called the REM, and that's a radiation equivalent for man. And what that does is it actually quantifies how much damage is done by a particular substance. And a REM for alpha radiation or beta radiation, even though the amount of radiation for one REM is different, the amount of damage that it would do when it says one REM is exactly the same. Now, when you're just living without coming in contact with anything special that has radiation associated with it, we are exposed to radiation from sunlight and from things in the soil and such. What we normally are exposed to is about 0.27 REM. And that's okay. We don't see any kind of damage from that that we can measure that is caused by that average baseline exposure. We start seeing biological effects when we are exposed to 25 REM. If you go higher than that, you're going to experience more damage. If you get above 100 REM, well, then you're going to start experiencing radiation sickness. LD50, and that's an important term, LD50 means the dose that will kill 50% of a population, which that's a significant amount of death. The LD50 for radiation is 500 REMs for humans. 600 REMs would probably kill most everyone. There are two other reactions that we're going to look at besides emission reactions, and that is nuclear fission and nuclear fusion. Fission is when a large nucleus will split into smaller nuclei. They're usually neutrons that are spit out along with the smaller nuclei. An example is shown here. Now they have a neutron coming in and hitting a uranium-235 nucleus. Some nuclei will undergo fission without the extra neutron coming in and bombarding the nucleus, but this is still fission. The neutron hits the uranium-235 nucleus, and then what happens is that nucleus splits apart and makes a krypton-91 nucleus and a barium-142 nucleus. And of course, 3 neutrons are split out of that nuclear mess and go flying out. And of course, there's lots and lots of energy that comes out of this along with that. You can see this is a balanced nuclear reaction because the mass is 91 plus 142 plus 3. Notice there's this a coefficient of 3 in front of those neutrons, so 3 neutrons come out. So 91 plus 142 plus 3 gives you 235 plus 1. 36 plus 56 gives you 92. So this is a balanced reaction. We have nuclear fusion, and fusion is a joining together of 2 tiny nuclei to form a slightly larger nucleus. An example of that is shown down here, where we have deuterium plus tritium colliding and making helium-4 plus a neutron. Notice that the sum of the masses on the reactant side is 5, and the sum of the masses on the product side is 5. The sum of the charge on the reactant side is 2, and the sum of the charge on the product side is 2. We are looking into using fusion to get energy for use here on Earth, but it is very hard to do that because fusion requires plasma, which is material that has been heated so high that the electrons no longer stay on the atoms, and what you have is nuclei swimming around and electrons off those nuclei and swimming around so that the nuclei can collide with each other. And those temperatures are so high that it's extremely hard to contain matter at that high temperature. The first thing that we need to do to balance this top reaction is to know what are all the masses and charges. So if I look at the neutrons, I know the mass of a neutron is 1 and the charge, so I can write those in. Next, let's go ahead and do the mass balancing. If I look at that, 134 plus 107 plus 3 gives me 244. Next, I need to know my charges on iodine and molybdenum, and I look them up and I see that iodine has a charge of 53 and molybdenum has a charge of 42. Gives me 95. Then I look on the periodic table for 95 and I find that is americium, and so I can write in its symbol. That is an example of fusion there. You can recognize it because it's one large nucleus making two smaller nucleus, plus there's some neutrons being sprayed out. Let's go ahead and look at the next reaction. In order to do that, we need to first know what is the mass and charge of that proton. 1 and 1. I also know that the charge on a hydrogen is 1 and the charge on a helium nucleus is 2. So this gives me that my particle that's missing must have a mass of 3, a charge of 2, and that is helium nucleus. Don't forget to do in-text problems as you read, and make sure you do the following end of chapter problems. The worksheets have good nuclear reaction problems and nuclear half-life problems, and there will be an online quiz posted for this chapter.